Part 2 of hydrogen and hydrogen-like systems. I would like to discuss the solution of the angular functions of hydrogen and hydrogen-like systems. The angular equation of hydrogen or hydrogen-like atoms is given by 1 by y theta phi sin theta into d by d theta sin theta d by d theta y psi theta phi plus 1 by psi y theta phi sin square theta into dou square by dou d phi square into y theta phi, that is equal to minus L into L plus 1. The solution to this equation 21 are the spherical harmonic functions. Here L is used in the separation constant. That is, the L is used as the same index as that of in the spherical harmonics, that is y Lm theta phi. In fact, it is the angular momentum quantum number L. By introducing the contribution of magnetic quantum number, these spherical harmonics are also separable. That is, the spherical harmonics y Lm theta phi, that is separated into psi Lm theta and psi m phi. We will use such a solution in the angular equation without the indices L and M until we see where they originate. By using this, the psi theta phi, that is written as psi theta into psi phi. By substituting this in equation 21, we get 1 by psi theta psi phi sin theta into dou by dou theta into sin theta dou by dou theta psi theta psi phi plus 1 by psi theta psi phi sin square theta into dou square by dou phi square into psi theta psi phi, that is equal to minus L into L plus 1. Here psi theta functions only on theta and psi phi functions only on phi, and therefore this equation can be written as 1 by psi theta into sin theta dou by dou theta sin theta dou by dou theta psi theta plus 1 by psi phi into sin square theta into dou square by dou phi square into psi phi, that is equal to L into L plus 1. Multiplying this equation by sin square theta and rearranging, we get sin theta by psi theta into dou by dou theta sin theta dou by dou theta psi theta plus L into L plus 1 into sin square theta plus 1 by psi phi into dou square by dou phi square into psi phi, that is equal to 0. The first two terms depends only on theta and the last term depends only on phi. Again, we get only non-trivial solutions to this equation in such a way that the right hand side of this equation, these two functions terms, that is the first two terms which depends only on theta and the another term that depends only on phi, these two are separately equal to another constant. Here we are using m square as the separation constant. By using the separation constant m square, we can write these two in two separate equations, that is sin theta by psi theta into dou by dou theta into sin theta dou by dou theta psi theta plus L into L plus 1 sin square theta, that is equal to m square, and 1 by psi phi into d square by d phi square into psi phi, that is equal to minus m square. And this shows how the magnetic quantum number is introduced, that is how the magnetic quantum number m is introduced. Again, the equations 24 and 25 is needed so that the sum is equal to 0, so that the separation constant must have opposite signs on the right hand side of the two equations 24 and 25. First we have to find out the solution for psi phi equation, that is azimuthal angle equations. So the azimuthal angle equation, that is 1 by psi phi into d square by d phi square into psi phi, that is equal to minus m square. And this is, if we write this equation is into 1 by psi phi into dou square by dou phi square into psi phi plus m square is equal to 0. It is a second order differential equation, and this gives the solution of psi phi, that is equal to e raised to im phi, where the subscript m is added to psi phi, because it is now clear that there are many solutions as there are allowed values of m. We can also show that psi m phi, that is equal to e raised to im phi, is a solution of equation 26 as follows. That is d square by d phi square into psi m phi, that is equal to d square by d phi square of e raised to im phi. That is taking the double differential of e raised to im phi. Then we can write, first we take the first differential, that is d by d phi of im into e raised to im phi, that is equal to, again, that is I square into m square into e raised to im phi, that is I square, we know that it is equal to minus 1, then minus m square, that is equal to psi m phi. Then the left hand side of the equation 25 becomes 1 by psi phi into dou square by d phi square psi phi, that is equal to 1 by psi phi minus m square into psi m phi, that is equal to minus m square. Therefore the solution can be written as psi m phi, that is equal to e raised to im phi, is a solution of equation 25. Next we have to find out the solution of the psi theta equation, that is polar angle equation, and this is more tedious. The polar equation, sin theta by psi phi into d by d theta sin theta d by d theta psi theta plus l into l plus 1 sin square theta is equal to m square, and this can be written as sin theta d by d theta sin theta d by d theta psi theta plus l into l plus 1 sin square theta into psi theta minus m square into sin psi theta, that is equal to 0, evaluating the first term. And the first term, that is sin theta by d theta sin theta d by d theta psi theta, that is equal to sin theta d by d theta into sin theta d psi theta by d theta, that is equal to sin theta into cos theta, taking the derivative, cos theta into d psi theta by d theta plus sin theta into d square by d theta square into psi theta, that is equal to sin square theta into d square by d theta square psi theta plus sin theta cos theta into d psi theta by d theta. So using this equation, the above equation becomes, that is 25, equation 27 becomes sin square theta d square by d theta square psi theta plus sin theta cos theta d psi theta by d theta plus l into l plus 1 sin square theta psi theta minus m square psi theta, that is equal to 0. Here next we are going to change the variables in such a way that the x is equal to cos theta, and we will comment this on later. When we substitute like this, we can represent the theta in terms of x. Therefore d psi theta by d theta, that is equal to d f of x by dx into dx by d theta, that is equal to d f of x by dx into minus sin theta, that is equal to minus sin theta into d f of x by dx, and the second derivative is d square by d theta square psi theta, that is equal to d by d theta of minus sin theta into d f x by dx, that is equal to minus cos theta into d f x by dx minus sin theta into d by d theta of d f x by dx, that is equal to minus cos theta into d f x by dx minus sin theta into d by dx of d by d theta of d f x by dx, that is equal to minus cos theta into d f x by dx minus sin theta into d by dx of minus sin theta into d by d f x by dx, or this is equal to minus cos theta into d f x by dx plus sin square theta into d square f x by dx square. Substituting these equations in the equation 28, we get sin square theta into sin square theta into d square f x by dx square minus cos theta into d f x by dx plus sin theta cos theta into minus sin theta d f x by dx plus l into l plus 1 sin square theta into f x minus m square into f x, that is equal to 0, which gives an equation both in theta and x, which is not formally appropriate. So dividing by sin square theta, we get sin square theta d square f x by dx square minus cos theta d f x by dx minus cos theta into dfx by dx plus L into L plus 1 into fx minus m square by sin square theta into fx, that is equal to 0. The change of variables is complete upon summing the two first derivatives using the equation cos theta is equal to x, or sin square theta is equal to 1 minus cos square theta, that is equal to 1 minus x square, since cos theta is equal to x square. So substitute these values, then we can get the equation as 1 minus x square into d square fx by dx square minus 2x into dfx by dx plus L into L plus 1 into fx minus m square by 1 minus x square into f of x, that is equal to 0. This equation is the associated Legendre's equation, which reduces to Legendre equation when m is equal to 0, and this equation is named after the French mathematician Henri Legendre. If the derivatives are indicated with primes, then the associated Legendre equation is often written as 1 minus x square f2 dash x minus 2x into f dash x plus L into L plus 1 fx minus m square divided by 1 minus x square into fx, and the Legendre equation becomes 1 minus x square f dash x f2 dash x minus 2x into f dash x plus L into L plus 1 into fx is equal to 0 when m is equal to 0. That is, the associated Legendre equation become Legendre equation when the value of m is equal to 0. The solutions to the associated Legendre equations are the associated Legendre polynomials or associated Legendre functions. That is the solution of fx, that is equal to p lm into x. The associated Legendre polynomial or functions p lmx are represented by p lm into x, that is equal to minus 1 raised to m into root of 1 minus x square raised to m dm by dx raised to m p lm x, where the L can take values 0, 1, 2, 3, etc. and m can take values minus L to plus L through 0. Similarly, the Legendre polynomials or Legendre functions are the solutions of Legendre equations and can be expressed as using the Rodriguez formula, that is p lx, that is equal to minus 1 raised to L into minus 1 raised to L divided by 2 raised to L into L factorial into dl by dx raised to L into 1 minus x square the whole raised to L. In general, the Legendre functions or polynomials are the solutions of Legendre differential equations that appear when we separate the variables of a Helmholtz equation or a Laplace equation or a Schrödinger equation using the spherical polar coordinate systems. The first few Legendre polynomials or functions are given in the table 1. p0x is equal to 1, p1x that is equal to x, p2x that is equal to 1 by 2 into 3x square minus 1, and p3x that is equal to 1 by 2, 5x cube minus 3x, p4x that is equal to 1 by 8 into 35x raised to 4 minus 30x square plus 3, and p5x that is equal to 1 by 8 into 63x cube x raised to 5 minus 70x cube plus 15x. And the Legendre polynomials are, some of the Legendre polynomials are given in this table. Thus, from the table it is clear that if the Legendre equation is same as the associated Legendre equation with m is equal to 0, the solutions to the two equations must be the same when m is equal to 0. That is, PL that is equal to PL0. Here the factor minus 1 raised to m indicated that the associated Legendre polynomials in order to make the sign of the all spherical harmonics as positive. Finally, the change of the variables x is equal to cos theta was done to put the differential equation in a more elementary form. That is, we get, for example, we can generating the function for spherical harmonic functions as y lm theta phi, that is equal to minus 1 raised to m square root of 2l plus 1 into l minus m factorial divided by 4 pi into l plus m factorial into p lm cos theta into e raised to im phi m, where when m greater than or equal to 0. and y lm L minus m theta phi, that is equal to y star lm theta phi if m less than 0, where rho p lm cos theta are the associated Legendre polynomials or functions. If we need spherical harmonics with m less than 0, we will calculate the spherical harmonics with absolute values of or modulus of m and then calculate the adjoint. In summary, we separated the angular equation into azimuthal and polar portion. The solutions of the azimuthal angle equation are the exponential including the magnetic moment quantum number. The solutions to the polar equations are the associated Legendre polynomials, which are the different for each choice of the orbital angular momentum and magnetic moment quantum number. Both quantum numbers are introduced into the respective differential equations as the separation constants. Since we assumed a product of two functions to get the solutions of azimuthal and polar part, the solutions to the original equation 21 are the product of two solutions, that is rho lm cos theta and e raised to im phi. All other equations in the above equations are simply normalization constant. The product rho lm cos theta e raised to im phi are the spherical harmonic functions. References: Quantum Chemistry, BK Prasad, New Age International Private Limited, and Chapter 10, The Hydrogen Atom, and it is from the Google website faculty.washington.edu.